Okay, great. Well, it's a pleasure to be here. I'm Jason Hogan. I'm a professor in the Department of Physics at Stanford University. And Mark Kasevich regrets that he couldn't be here. I'm happy to fill in. I've been working with Mark for many years at Stanford on developing precision inertial sensors, accelerometers and gyroscopes and things like that, using this technology of atom interferometry. And for a number of years now, we've been collaborating with NASA Goddard Space Flight Center on developing this technology or applying this technology towards gravitational wave detection. So I want to tell you a little bit about our technology and our ideas for how to make a gravity wave detector. Okay, great. So first of all, let me try to motivate this science. So why are we interested in gravitational waves? So turns out most of what we know that we've learned observationally about the universe necessarily comes from electromagnetic radiation, from light. Different kinds of telescopes and different wavelength ranges. That's how we've learned about what's out there. And so you can think about gravitational waves as essentially, we like to say poetically, the soundtrack of the universe. It's another aspect of the universe that we haven't been able to detect using light. And so gravitational waves are ripples in space-time that propagate away from violent events that occur out there, and they can come to our detectors, and you can think of them sort of as representing, sort of analogous to sound in the sense that it's different than light and can give us information in a new way. And this is an example of this is an artist's rendition of what a source of gravitational waves might look like. These are intended to be two compact objects you can imagine, neutron stars or even black holes that are spiraling around each other. They're orbiting around, and the orbits are decaying, and as they spin around each other, they distort space-time, and those fluctuations in space-time propagate away at the speed of light, and then can come and we can then observe them. So in addition to being a new way to look at things, it can tell us things about the universe that we can't see with light. You can imagine objects that are dark in some sense. They don't emit light, but that would emit gravitational waves. Also, you can think about these as laboratories for extreme gravity. This is some of the most violent events in the universe, and by studying them, you can learn about whether general relativity works at the strongest scales. And then finally, there's interest in learning about cosmology by studying gravitational waves, because it turns out they let you look back further in time than you can with light, to the very first instance of the universe, beyond the surface of last scattering. So what does a gravitational wave look like? How can we build a detector? This should go. Yeah. So first you have to understand what an incoming gravitational wave does to matter, and that's how we can design our detectors around that principle. So if you imagine, just a thought experiment, putting an array of rocks in a ring, as shown here, this ring of rocks, just sort of put them up, just test masses in a circle. If a gravitational wave were to come out of the screen towards us or away from us, it would cause the ring to distort in the way that you see animated here. It causes the diameter of the ring to distort. And so that's the effect on sort of freely falling objects. And so you can ask, how big is this effect? This is clearly exaggerated here. So if you think just of two objects, these black spheres here, and it turns out that the amplitude of oscillation is proportional to how far apart you separate them. And h here is the strain of the gravitational wave. That's how strong the wave that we're trying to see is. And so just as a rough example, if you separate your two objects by 1,000 kilometers, the wiggle amplitude is about a femtometer, 10 to the minus 15 meters, or about the diameter of a proton. So it's extremely small, and that's why this is such a hard problem. And so what we need is extreme sensitivity to have ever a hope of seeing such a small effect. Okay, so there we go. So the conventional approach has been developed for many years. It uses laser interferometers. And so shown here is on the top pane is the LIGO interferometer you may have heard about, and it's a Michelson interferometer with two arms perpendicular to each other. And the idea here is that these mirrors, which are shown here, sort of hanging from these blue anchors, these two circular mirrors, are your test masses, and the gravitational wave will cause those mirrors to wiggle. And you need two pairs perpendicular, and you can measure the wave coming in that way. The reason you need two, it turns out, is because to measure this distance using light, you'd need an extremely stable wavelength, and you can't build a laser that good. And so they have this really nice trick where, since the laser is too noisy, you send this noisy laser simultaneously down two perpendicular arms, and that noise is then common to the two halves of the two arms of the interferometer, whereas the gravitational wave signal is differential, and it adds when you subtract the two arm length variations. So that's a nice trick, and that's how LIGO and advanced LIGO will work. And those, it turns out, are really good at seeing what we call high-frequency gravitational waves, sort of above 10 hertz. They really are on the audio spectrum. And so that's going to be really exciting when that comes online in the next year or so. For lower frequency, it turns out you really want to go into space. This is a rendering of the LISA concept, which is a satellite-based test or gravitational wave detector concept based on 3 satellites with laser ranging between them. And for the same reason that LIGO has 2 arms, LISA needs 3 satellites in order to have non-parallel arms to compare. And so that's kind of the range of frequencies that I want to talk to you about applying atom interferometry to. So by means of introduction, let me give you an analogy or describing atom interferometry. Let me try to compare it to something you're familiar with. On the upper plane here, I have an example of a light interferometer. You can take light and send it through a beam splitter, which causes the light to travel along an upper path and a lower path. You can use a couple of mirrors and send that light back to a second beam splitter where you can get interference. This is totally conventional Mach-Zehnder interferometer geometry. And so if you put a couple of detectors at the output of those, the 2 ports in the interferometer, you can learn something about the relative path lengths, the relative optical path lengths that the light takes along those 2 arms. And if you look, for example, at one of these detectors, you might see something that looks like these light fringes I've shown here, circular interference pattern, where the light and the dark regions represent constructive and destructive interference of light. So in the same way we can do that with an atom, quantum mechanics tells us that atoms are waves, that we can use the wave-like nature of atoms to make interference experiments. And so here the atom is shown as a solid black line, and we have to implement a beam splitter for atoms, shown here. If we can split the atom into an upper and a lower path, we can bring the 2 halves back together and interfere them with a second beam splitter. So I haven't told you how we do that, but if you send an atom along 2 arms like that, you can measure an interference pattern in the same way. You can see here this figure here called atom fringes. The blue and red regions of this picture indicate regions of constructive and destructive interference, in this case of atom de Broglie waves. So it's the same concept, but now instead of light, we're using atom waves. And so it turns out that that's a great way to make a precision, in this case, accelerometer. The phase that you read out by looking at that fringe pattern tells you about the acceleration that the atom felt during the sequence. Let's see if that goes. Yeah. So in a little bit more detail, I have to tell you how we actually implement those atom optics, those beam splitters and mirrors for the atom to implement this interferometer. And so all the work we do on our Earth test systems are in vertical geometry, like this. You can see this is supposed to be a cross-section of a vacuum tube. We've got some atoms shown as this little blue ball, and the atoms are in free fall, for example. And so while the atom is falling, we can implement these interferometer beam splitters using laser pulses, shown as these pink arrows. And the lasers come in, and since light carries momentum, we can actually transfer momentum to the atom using the light, and that's how we implement this splitting process. And so you can see the same diagram again with a little bit more detail. On the y-axis is the height that the atom is of the atom as a function of the time on the horizontal axis. And so the atom is just in free fall, except at the initial time we apply this pulse of light, shown as a squiggly line here, and that pulse of light transfers momentum to half of the atom, speeding it up, and so we get then half of the atom is traveling faster than the lower half, and you get actually a spatial separation between the 2 halves. And just to give you a sense of that this is a real physical separation, this picture down here this is a picture taken of the atom at the midpoint here, at the halfway point, when the atom is maximally separated. So we have an atom, we've split it vertically, and then we take a picture, and that collapses the quantum wave function. And this picture tells you what the probability distribution that the atom had at the moment of that picture. And so you can see that we've got half of the atom is over here and half is over there, and it's separated by 4 centimeters. And so that brings me to my second point. In order to make these sensors really precise or really sensitive, it turns out we want to make the area of this interferometer as big as possible. So that means we want the duration along the horizontal axis, we want the time that the atoms are split to be as long as possible, and we want the vertical separation between the two halves of the atom to be as big as possible. And so this is 4 centimeters here, and I'll show you work where we're pushing that to even higher numbers. So this is just some pictures of what our apparatus at Stanford looks like for doing these experiments. We've got a 10-meter tall vacuum chamber where the atoms are falling. You can see that here. There's a vacuum tube the atoms fall in. There's a source of atoms at the bottom that produces Bose-Einstein condensates of rubidium in this case. We launch those atoms at about 13 meters per second into this vertical tube where they fall for about 2.5 seconds. They have to be really cold so we can watch them for a long time. So the atoms are at 3 nanokelvin temperature. And then we do the interferometry while they're in free fall inside this magnetically shielded region. So this is, I think this next slide is some of our early results with the first interferometers that we performed in this experiment, in this apparatus I'm showing you here. Let's see if that goes. There we go. Once again, I've got a little interferometer cartoon here shown with, we got a lower arm and an upper arm. And if we take a picture at the end of this interferometer, we see something that looks like this upper picture labeled port 1 and port 2. And those green blobs represent atoms. That's how many atoms that we see on our detector. And so that's how we make our measurement. We count how many atoms are in each of those 2 ports. And so if you look, for example, at this series of pictures on the bottom plane, when the phase shift in the interferometer, the relative phase between the upper and the lower arm of the interferometer, for example, is varied, you can see the number of atoms that show up in the upper half of the picture versus the lower half of the picture varies sinusoidally as a function of that phase. And so by looking at these pictures, we can determine what the phase shift that the atom felt during that interferometer. And that, in this case, tells us about the acceleration that the atom felt. And just to give you some sense of how sensitive is this accelerometer, this was we were going for maximum sensitivity here, so the duration of this interferometer was over 2 seconds long, where the atom was in this quantum superposition. And the sensitivity ends up being about 7 × 10⁻12 G each time we do one of these experiments. So each shot is giving us that resolution in acceleration. And so that's one of the best accelerometers you can make. So how can we do better? That's already pretty exciting, and we were thinking that would be great for applying towards this problem of gravitational wave detection. But as I mentioned, one of the ways we can enhance the sensitivity even more is by increasing the separation between the 2 halves of the atom. And so for that last data set I just showed you, the atoms are separated by a little over 1 centimeter. So to get them separated by more, the trick is to use more momentum, right? So we get the splitting by transferring momentum from the light to the atom using these pulses of light. And so there's nothing stopping us from just adding additional pulses. And so this cartoon here at the bottom shows what the sequences we do kind of look like. We have all these squiggly lines are laser pulses. So the first laser pulse at t = 0, for example, that's the initial one that splits the 2 halves. That's the conventional interferometer beam splitter. But then we can come in with these additional 2 pulses, for example, here, shown as additional squiggly lines, and those add more momentum. Each pulse adds 2 h-bar k of momentum, h-bar k, the momentum of a single photon. And so we want to increase that as much as we can. And so this picture that I'm showing you right here is a snapshot at the midpoint of an interferometer where we've added additional pulses. That should click over. And so this is our latest record. This is the biggest separation we've been able to achieve by using 30 h-bar k, so many pulses of light. We were able to get 18 centimeters separation vertically between the 2 halves of the atom. So I think this is already a pretty exciting thing to think about. This is an atom that's simultaneously it's here and here, so it's about 7 inches across. There's an atom that's simultaneously in both of those places. That's what quantum mechanics tells us. And yet we're able to bring those two halves of the atom back together and see robust interference. So it really is, I think, pretty exciting that quantum mechanics lets us do that with this system. Great. So now, can we apply this? And I should mention that would have about 15 times the sensitivity of acceleration sensitivity from the data that I showed you. So that enhancement in wave packet separation gives us an immediate increased sensitivity. Great. So can we apply that to this problem of gravitational wave detection? Other than having this tool that I just described you, atom interferometry, there are some other reasons why atoms present a really interesting approach to this problem. And basically it comes down to neutral atoms are really good gravitational test particles. Since they're neutral, they don't react strongly to electromagnetic fields, so you're sort of shielded intrinsically from perturbative effects. I guess another point which I'll come to in a couple of slides, which isn't obvious from the rest of the talk, is that we think atoms give us the ability to build a gravitational wave detector using a single linear baseline. You recall I described LIGO has its 2 arms. LISA was this triangle configuration. And with an atom interferometer, you could build a single linear detector. And that has some advantages, we think, for potentially for cost and complexity. So let's go to the next slide. So this is what a cartoon of an atom-based gravitational wave detector would look like. As I mentioned, there's going to be one baseline that's shown on this, shown across the top here. So you'd have imagine a source of atoms on the left, a source of atoms on the right, and this pink line between the two represents the laser pulses that we'd be sending back and forth, and those laser pulses would implement the atom interferometer. So you'd implement an atom interferometer on each end of this long baseline. And so you could see an artist's rendition of what that might look like here in orbit around the Earth. Different orbits are certainly possible. For a LEO orbit, it would look something like this, where these 2 little white stars represent the atoms. Let's go to the next slide. Okay, so this is a little bit more the technical details of how that would look. I won't go into all the detail here. The data and experiments I've been telling you about have been using rubidium atoms. We developed a scheme using a different kind of atoms, in this case alkaline earth-like atoms, like for example strontium or ytterbium, where we can get away with this single baseline gravitational wave detector. It's essentially using the technology used by atomic clocks. You may know over the years, atomic clocks are getting better and better. They're now at the point where the fractional frequency stability is approaching 10 to the minus 18. What that means is that with an atomic clock, you only lose a second over the lifetime of the universe. Right? So these are really precise sensors, and that comes down to the existence of these great transitions as outlined, or as shown in this red line. I won't go into the atomic physics of it, but we think we can exploit that same transition that they use in atomic clocks to build an excellent gravitational wave detector that's at first order immune to laser frequency noise. And that's what lets us get away with building a single baseline rather than having multiple baselines. And just to sort of reiterate that, in the LISA configuration, you need 3 satellites. You need a triangle in order to have common mode rejection of laser frequency noise. With the proposal I'm describing here, with this laser frequency noise immune atom interferometry approach, you only need 2 satellites in a linear geometry, and that's, we think, could be a big advantage. And the reason that is, without going into all the details, is that these squiggly lines, once again, the laser pulses, are shared by the atom interferometer on the left and on the right. So whatever noise is on that laser, turns out, is going to be common to the 2 atoms. And so when you look at the difference between the 2, to look at the relative acceleration, that noise drops out. Let's go to the next slide. So this is the strain sensitivity curves. This tells you how sensitive to gravitational waves could such a sensor be, given some parameters that we've been thinking about. So the strain sensitivity is shown on the vertical axis. And so this is compared to, you can see this dashed line is what the LISA concept is. And you can do an amazing amount of exciting science in the millihertz band with that, all sorts of in-spirals and of different kinds are visible. And you can see with this green curve is an atom-based approach using very conservative parameters. Basically, just to compare to what I showed you earlier, this is the first data set I showed you with the sensitivity we've already demonstrated in the lab, at least for a single accelerometer. We could use that level of atom optics to do this sensor, and we'd get sensitivity comparable to LISA. So we think that's pretty exciting. But even more exciting is that using so-called 12 photon or 12 h-bar-K beam splitters, this blue curve, you can get up to 10 times better than LISA in some frequency ranges. Just for reference, once again, I showed you data where we demonstrated 30 h-bar-K, and so this is, compared to that, even a little conservative. So we think that there's a lot of overhead and room for improvement with this technology, sort of already in the range where we're starting to demonstrate in the lab, and you can get some pretty exciting sensitivity curves. Let's go to the next slide. So a little bit more the technical detail of how you would build such a sensor. I don't have time to go into all this. Just to mention, you have your two satellites with atoms sort of living inside, and you send laser pulses back and forth between the two. One of the problems you have to deal with is diffraction. If the baseline is really long, the light will spread out and it won't be very strong when it reaches the other side. So we developed an approach that uses a local amplification where we measure the phase of the incoming light and do a heterodyne lock to that light to provide enough laser power to drive the transitions. So our preliminary estimates of the laser frequency noise requirements, timing jitter requirements are very modest. And in particular, since the atoms are freely falling and our laser noise is common, we can get away with excellent or very, very modest satellite bus requirements. So shown down here, sort of microns per root hertz for linear motion and sort of microradians per root hertz for angular jitter. So it doesn't need to be a drag-free satellite, for example. Now let's go to the next slide. You can also look at the Earth with this technology. Instead of looking at the universe, you can point it at the Earth and study Earth science. Just as an example, this is there's a instrument incubator project that's set up to analyze this this idea that's being there's an instrument being built by Aeosense Incorporated, where they're trying to use atoms to do what the GRACE mission did. GRACE is a microwave ranging experiment that is able to study Earth's gravitational field. And so this is an example of what you could do with an atom interferometer. For example, studying the water distribution on the Earth by looking for mass anomalies associated with water. And you could see as small as centimeter equivalent water heights with this. So we think that that's a pretty exciting direction to go as well. Let's go to the next slide. And I wanted to just end off my talk with one last thing we've been working on. For all these ideas to work in space, you need really cold atoms, even colder than what we use in the lab. And so we did some work recently to demonstrate extremely cold atoms using this approach, which we call lensing. Basically, it's in the same way you can collimate a beam of light using a glass lens, you can collimate a divergent cloud of atoms using a harmonic potential. And so if we go to the next slide. So we apply an optical pulse which acts like a harmonic restoring force we can actually use to collimate a beam of atoms that's diverging, and that effectively cools it. And so you can see if we don't apply our lens, we have an atom cloud that looks like this. When we apply a lens, we get a very sharp, narrow atom cloud, which indicates that it's been focused. Can we go to the next slide? And so we can vary the focal length of our lens by changing the duration of our laser pulse, which allows us to either refocus the cloud or to collimate the cloud. And if you go to the next slide, at the collimation condition, this represents an atom cloud with a temperature, or transverse temperature, effective temperature, I should say, of about 50 picokelvin. And so this is some of the coldest kinetic temperatures that have ever been observed, as far as we know. And we can use that in all of these ideas that I was telling you about. Next slide. Just wanted to put up all my many collaborators, and once again acknowledge the support we have from a NIAC fellowship for a number of years, and recently from the Keck Foundation towards pursuing these ideas. So with that, we can take some questions. I've got about 5 minutes.
Do you need? I mean, do you need electronics that operates close to in the 1 degree Kelvin to work with this?
Oh, that's a great question. Yeah. The question is, do the electronics need to be cold? So, for example, in the experiments that I was showing you, the data that I showed you, all of the electronics, all of the hardware is at room temperature. The only thing that's cold is the atom cloud. So the atom cloud we trap it using magnetic fields or optical fields, so it's not in thermal contact with the environment. So you can have room temperature around, and the atoms are still at sort of the nanokelvin temperature range. So you don't need particularly cold electronics.
So does that mean that the power output, I guess my question is, when you have very small signals and your electronics is far away, then you can lose your signal. Do you have that issue?
So we're generally limited, the noise is generally limited by the atom shot noise, it turns out. So just the number of atoms limits us. So we can get below these sort of other types of noise sources, electronics noise sources, generally pretty well, even at room temperature. But what we're limited by is the shot noise statistics. So the more atoms we have, the better we can determine what the phase shift is. So it's really all about getting big clouds of atoms.
So the other, I guess, question, or theoretical kind of question I had was, are you interested in seeing like low mass atoms? I mean, I don't know much about this, but I'd assume that it'd be preferable to have atoms that were really low mass, that would respond a lot to
it's interesting.
quick gravitational waves, and I see the mass of the atoms that you're using is actually pretty large.
Well, so it's interesting. I mean, to first order, you can think about this as an accelerometer. So we're measuring accelerations, and then the mass it doesn't really come into our first order signal. So it turns out the mass doesn't matter for that, at least at the first order. Where it actually can come in, it turns out bigger mass can actually help. Rather than hurt in some situations, because the wave packet separation is proportional to how much mass you have. And so a more massive atom won't separate as much for the same sensitivity. And so at some of these ideas, we're starting to be limited by the satellite size. If we split the atom by tens of centimeters or meters, we have to build a bigger box to put it in. So a bigger mass of atoms can lower that.
Thank you.
I just had one question.
Sure.
Do you have to worry about the radiation environment of space? I'm just thinking that there's a sun and that's going to be blasting you with 1,000 watts of photons. And what do those do?
Right, so the question is about solar radiation, and does that impact the ability for the sensor to work? And the answer is, in some situations, yes. For the designs I showed you, no. We have to shield the atoms from the sun. There's enough sunlight to essentially cause decoherence in the cloud. The atoms will absorb that light. It actually depends on the atom. Certain atoms, like for example, mercury, has a transition that is sort of hidden from the sunlight in some senses, and so you might be able to even operate such a sensor in free space without any kind of shielding. For some of the ideas that I put up here with this heterodyne link, we imagine having the atom in a box that's protected from the sun. Yeah. Great. Okay, well, if there's no more questions.